Standing under a night sky, have you ever felt that strange tug of wonder, that quiet sense that the universe is moving, shifting, expanding beyond what our eyes can see? It's not just an illusion. Every star, every galaxy, even the emptiness between them is caught in a vast, invisible current, carrying everything we know deeper into the cosmos. But here's the real mystery. Where is it all going? This isn't just a question for astronomers. It's a puzzle that touches the very heart of existence. And today, we're setting sail on that cosmic ocean, tracing the paths of galaxies to uncover the forces that guide them. Think of the universe as a storybook with pages still being written. 14 billion years ago, the Big Bang flung everything into motion, but that was only the first chapter. Since then, galaxies have raced away from one another like fragments of a shattered mirror, and the space between them stretches wider every second. But why? What unseen hand is pulling them apart? The answer lies in the hidden fabric of reality itself, a dark energy, a force so mysterious it makes up nearly 70% of the universe, yet we've never directly seen it. It's the engine behind the universe's accelerating expansion, and it's rewriting our understanding of where everything is headed. But this journey isn't just about distant galaxies or abstract forces. It's about our place in a cosmos that's forever in motion. Will the universe keep expanding forever, leaving galaxies isolated in an ocean of darkness? Or could there be a twist in the tale, a cosmic reversal we haven't yet imagined? The answers are out there, woven into the light of ancient stars and the whispers of empty space. So let's dive deep from the echoes of the Big Bang to the edge of what science can explain. By the time we're done, you won't just see the night sky differently. You'll feel it, alive with motion and mystery, pulling us all toward an unknown horizon. The Big Bang wasn't just an explosion, it was the birth of reality itself. Picture this, a single point of infinite density and heat, smaller than an atom, suddenly unleashing all the energy that would ever exist. In less than a second, space itself stretched faster than light, carrying matter and radiation outward in a fireball so hot that atoms couldn't even form yet. For hundreds of thousands of years, the universe was a swirling plasma, so dense that light couldn't escape. Then, finally, it cooled enough for the first hydrogen atoms to appear, and the cosmic fog lifted. That moment, nearly 14 billion years ago, is still visible today, not as a fading echo, but as a faint glow that fills every corner of the sky. We call it the cosmic microwave background, and it's like a snapshot of the universe's first baby photo, taken when it was just 380,000 years old. But here's what's truly mind-bending. That ancient light isn't just a relic, it's a map. Tiny variations in its temperature, fluctuations smaller than 1 part in 100,000 reveal where matter began clumping together, seeding the future homes of galaxies. Without those imperfections, gravity would have had nothing to work with, and the universe might have remained a featureless sea of gas. Instead, those tiny ripples grew over eons, pulled by gravity into vast cosmic webs, with galaxies strung along them like pearls on invisible strings. And yet, the story doesn't end there. That initial expansion never stopped. Space kept stretching, carrying galaxies farther apart, but something unexpected happened. The universe didn't just keep coasting. About 5 billion years ago, it started accelerating, as if some invisible force was pushing it apart faster and faster. That's the mystery of dark energy, a puzzle written into the very fabric of space. The same cosmic background radiation that shows us the universe's infancy also hints at its fate. Will dark energy keep stretching space until galaxies vanish over the horizon, leaving our night sky empty? Or could the universe collapse back in on itself in a cosmic reversal? For now, those answers are still written in the stars, waiting to be decoded. The night sky had always seemed eternal, a fixed tapestry of stars unchanging across generations. That was until Edwin Hubble pointed his telescope at distant galaxies in the 1920s and shattered humanity's oldest assumption. What he saw defied logic. Nearly every galaxy was racing away from our own, not randomly, but with a terrifying precision. The farther away a galaxy was, the faster it seemed to flee, as if space itself were stretching like the surface of an inflating balloon. This wasn't just motion, it was evidence that the universe was growing, evolving, alive in a way no one had dared to imagine. Hubble's discovery didn't just rewrite textbooks, it tore up the very idea of a static, unchanging cosmos. Before him, even Einstein had assumed the universe was eternal and unmoving, tweaking his equations to avoid the possibility of expansion. But the data was undeniable. Those fleeing galaxies carried a message. The universe had a beginning, and with it, perhaps an end. Suddenly, cosmology wasn't just about mapping stars. It was about reading the cosmic clock, measuring how much time had passed since everything began, and guessing how much might remain. Yet Hubble's revelation opened deeper mysteries. If galaxies are all racing apart, what launched them? Was it the lingering momentum of the Big Bang, like debris flung from an explosion? Or was something else, some invisible force, pushing them faster as time went on? The answers would lie in the faint light of supernova billions of light years away, in the way their light stretched and reddened as space expanded beneath them. Decades later, astronomers would discover that the universe wasn't just expanding, it was accelerating, a finding so bizarre it earned them the Nobel Prize. But here's the haunting question Hubble's work left us with: where does it all lead? If space keeps stretching, will there come a day when distant galaxies vanish over the cosmic horizon, their light stretched too thin to ever reach us? Or could the expansion slow, reverse, and collapse everything back into a single point? For now, the universe keeps its secrets, but every telescope trained on the night sky brings us closer to understanding whether we're sailing toward an endless sea of darkness or something stranger still. In the late 1990s, astronomers made a discovery so shocking it turned cosmology upside down. They were measuring the light from distant supernova, exploding stars so bright they can outshine entire galaxies, hoping to calculate how much the universe's expansion had slowed over time. But the data told a different story entirely. Instead of slowing down, the universe was speeding up, as if some unseen hand were pressing harder on the cosmic gas pedal with each passing moment. The implications were staggering. Whatever this force was, it wasn't just winning against gravity, it was rewriting the rules of the game. We call it dark energy, but that name barely scratches the surface of its mystery. Imagine pouring water into a glass, only to watch the water level rise faster the more you pour, defying every law you know. That's dark energy's effect on the cosmos. It makes up nearly 70% of the universe's total energy, yet we can't see it, touch it, or even detect it directly. All we know is its fingerprint, the way it stretches space itself, forcing galaxies to flee from one another at ever-increasing speeds. Some theories suggest it's woven into the vacuum of space, a property of nothingness that somehow pushes everything apart. Others propose it's an entirely new kind of field or particle, one that behaves unlike anything in our current physics textbooks. But the real question isn't just what dark energy is, it's what it will do next. Right now, its push is gentle enough that galaxies can hold themselves together. But what if it grows stronger? One terrifying possibility is the Big Rip, a scenario where dark energy's grip becomes so overpowering that it tears apart stars, planets, even atoms themselves, reducing the universe to a cold sea of disconnected particles. On the other hand, dark energy might fade over time, allowing gravity to regain control and pull everything back into a fiery collapse. Or perhaps it will continue exactly as it is, stretching the cosmos into an endless, thinning void where galaxies become so distant their light can never reach us again. The strangest part, dark energy's effects weren't always in charge. For the first 9 billion years after the Big Bang, gravity dominated, slowing the expansion as matter clumped into galaxies and clusters. But around 5 billion years ago, dark energy took over, and we still don't know why. Was there a cosmic switch flipped somewhere in the fabric of reality? Or is this acceleration just the universe's natural rhythm, a phase we're only now beginning to understand? Every observation, from the cosmic microwave background to the distribution of galaxies, adds another piece to this puzzle, but the full picture remains maddeningly out of reach. One thing's certain, dark energy isn't just a curiosity for scientists, it's the architect of our cosmic future. Whether it leads to a frozen emptiness, a catastrophic collapse, or something beyond our current imagination, it holds the answer to the ultimate question of where everything in the universe is going. And until we solve its secrets, the fate of reality itself hangs in the balance. Picture the universe billions of years from now, not as a vibrant tapestry of galaxies, but as a vast, silent graveyard. This is the Big Freeze, a fate so chilling it makes black holes seem warm by comparison. As dark energy relentlessly stretches space, galaxies will vanish over the cosmic horizon one by one, their light stretched too thin to ever reach us. The night sky, once glittering with stars, will grow darker with each passing eon until only our own Milky Way remains visible, a lonely island in an ocean of nothingness. But the darkness is just the beginning. As the universe expands, the very fuel for star formation, cosmic gas and dust, will become so spread out that new stars can no longer ignite. One by one, existing stars will exhaust their fuel, some exploding in supernova, others fading into dense white dwarfs or collapsing into black holes. Over trillions of years, even these remnants will decay. Black holes will slowly evaporate through Hawking radiation, leaving behind only faint whispers of energy in an otherwise empty void. The temperature of the universe will plummet toward absolute zero, the coldest possible state where all motion ceases. It's a fate so bleak that even time itself may lose meaning, with no events left to mark its passage. Yet the Big Freeze isn't just a distant horror story, it's a puzzle that forces us to rethink the nature of reality. Why would the universe, born in a fireball of unimaginable heat, end in such icy stillness? Some theories suggest dark energy could evolve, its strength changing over time in ways we don't yet understand. Others propose that our universe is just one bubble in a multiverse, each with its own rules and fate. There's even a haunting possibility that the Big Freeze isn't the end but a prelude to something stranger. A quantum fluctuation could spark a new Big Bang, birthing an entirely new cosmos from the frozen ashes of our own. For now, the evidence points toward the Big Freeze as the most likely outcome, but cosmology has taught us to expect the unexpected. Every discovery, from the accelerating expansion to the mysteries of dark matter, has rewritten our understanding of the universe's destiny. The only certainty is that the cosmos never ceases to surprise us, and that makes the search for answers all the more thrilling. For centuries, the idea of an endlessly repeating universe has captivated thinkers, from ancient philosophers to modern physicists. Before we discovered dark energy's relentless push, there was a compelling case for the Big Crunch, a dramatic finale where gravity would finally overcome expansion, dragging every galaxy, star, and atom back into a single, searing point. Picture it, the universe's grand story ending where it began, collapsing like a house of cards until space and time themselves fold inward. In this scenario, the Big Crunch wouldn't just be an end, it could be a reset button, triggering another Big Bang and birthing a new cosmos from the ashes of the old. A never-ending cycle of creation and destruction, like a cosmic heartbeat. The math behind this idea is eerily beautiful. If the universe had just a little more matter, enough for gravity's pull to outweigh expansion, galaxies would eventually slow their flight, pause, and then rush back toward one another. Clusters would collide, temperatures would soar, and the cosmos would heat up until even atoms ripped apart. The final moments would mirror the Big Bang's chaos, a fiery symmetry where the end becomes another beginning. Some theories even suggest these cycles could explain fine-tuning in our universe's laws, each iteration tweaking the constant slightly until conditions perfect for life emerge. But dark energy changed everything. Its discovery revealed an expansion that isn't just continuing, it's accelerating, like a car pressing the gas pedal harder with time. That makes the Big Crunch seem unlikely today, but the universe has surprised us before. What if dark energy isn't constant? Some models propose it could decay over time, weakening until gravity regains the upper hand. Others imagine a more exotic possibility. Dark energy might flip its behavior, transforming from a repulsive force into an attractive one, like a magnet reversing its poles. If that happened, the collapse could be inevitable. There's a haunting poetry to the Big Crunch idea, a universe that breathes in and out, eternally renewing itself. Yet the evidence we have now points away from it, toward an ever-expanding fate. Still, cosmology teaches us humility. Every major discovery, from Hubble's expanding universe to dark energy's acceleration, has rewritten our expectations. Maybe the final chapter of the universe's story hasn't been decided yet, or perhaps in some distant future, gravity will stage a comeback, pulling the cosmos back toward a fiery rebirth. Until we know for sure, the mystery remains a reminder that even the universe's fate is a story still being written. The most violent fate the universe could face isn't fire or ice, it's being torn apart from the inside. Imagine dark energy not just pushing galaxies apart, but growing stronger over time until its grip becomes unstoppable. First, galaxy clusters would be ripped from one another, then individual galaxies shredded into wandering stars. But the horror wouldn't stop there. As space itself stretched faster than the forces holding matter together, stars would explode as their gravity lost the battle against the expanding void. Planets would unravel next, their atoms scattered like dust in a cosmic hurricane. Finally, in the last microseconds of existence, even atomic nuclei, the building blocks of reality, would be split apart, leaving nothing but a soup of quarks and radiation. This is the Big Rip, and it's not just a nightmare scenario, it's a real possibility hiding in the equations of cosmology. What makes this idea so chilling isn't just the destruction, but the timing. If dark energy behaves in a certain way, what scientists call phantom energy, it could trigger the Big Rip in as little as 22 billion years. That might sound like an eternity, but on cosmic scales, it's shockingly soon. Our sun will still be a cooling white dwarf remnant when the first signs appear. Galaxies at the edge of the observable universe blinking out of sight as space stretches faster than light can cross it. From there, the end would come swiftly. In the final months, stars would vanish from the night sky. In the last minutes, planets would disintegrate. And in the final instant, the fabric of spacetime itself would rupture, leaving no structure, no memory, no trace that anything had ever existed. Yet the Big Rip isn't inevitable. It all hinges on a single, unanswered question. Does dark energy's strength remain constant, or does it intensify as space expands? Right now, the evidence is frustratingly vague. Observations of distant supernova and galaxy clusters suggest dark energy behaves like Einstein's cosmological constant, a steady force that doesn't change over time. But alternative theories like quintessence propose it could evolve, growing stronger or weaker based on conditions we don't yet understand. If it strengthens even slightly, the Big Rip becomes a ticking clock. If it weakens, the universe might escape this fate entirely. There's a haunting irony here. Dark energy, which makes up most of the universe's energy, remains almost entirely mysterious. We see its effects, the way it stretches galaxies apart, but we don't know what it is, why it exists, or whether its power is fixed or growing. Every telescope pointed at the cosmos, from the James Webb Space Telescope to upcoming projects like the Vera Rubin Observatory, is hunting for clues. They're measuring the expansion rate with unprecedented precision, searching for tiny variations that could reveal dark energy's true nature. For now, the Big Rip remains one of several possible endings to the cosmic story. But it serves as a stark reminder. The universe isn't just expanding, it's evolving, governed by forces we're only beginning to comprehend. Whether it ends in a whisper, a crunch, or a rip, one thing is certain: the final chapter hasn't been written yet. And that means we still have time to uncover the truth. Just after the Big Bang, in the tiniest sliver of time imaginable, something extraordinary happened. The universe didn't just expand. It exploded outward faster than light itself. This wasn't the steady stretching we see today, but a runaway growth spurt called cosmic inflation, where space doubled in size over and over again, like a balloon inflating trillions of times in less than a blink. In that fleeting instant, the entire observable universe grew from smaller than an atom to the size of a grapefruit, seeding the vast cosmos we know today. What's truly wild about inflation isn't just the speed, it's the fingerprints it left behind. Without it, the universe would look like a chaotic patchwork of hot and cold spots. Instead, the cosmic microwave background, the faint glow from the early universe, is almost perfectly smooth with only tiny ripples. Those ripples are crucial. They're the quantum fluctuations from inflation stretched across the sky, the seeds that gravity would later mold into galaxies and galaxy clusters. In a way, every structure we see today, from the Milky Way to the farthest quasars, owes its existence to those microscopic quantum jitters magnified by inflation's explosive expansion. But here's where things get even stranger. Some theories suggest inflation never truly stopped, it just paused in our corner of reality. Imagine a bubbling pot of water, where each steam bubble is a new universe inflating into existence, complete with its own laws of physics. This is the idea of eternal inflation, a multiverse where universes sprout endlessly, each one a self-contained cosmos with its own unique properties. Our universe might be just one bubble in an infinite froth of realities, some with stronger gravity, others with no stars at all, or even dimensions we can't begin to imagine. The implications are staggering. If eternal inflation is real, the constants of nature, the speed of light, the strength of gravity, might not be fundamental truths but mere accidents of our particular bubble. Elsewhere, physics could be utterly alien. Some universes might collapse instantly, others could be so empty that life never emerges. It's a humbling thought. What we call the universe might be an inconceivably small fraction of a much grander, weirder reality. Yet for all its elegance, inflation isn't a done deal. While it explains the universe's smoothness and structure beautifully, we still lack direct proof. The hunt for gravitational waves from inflation's aftermath, ripples in spacetime from that primordial growth spurt could be the smoking gun. Detecting them would give us a glimpse into the universe's first moments, a window onto physics at energies so high we'll never recreate them in a lab. Until then, inflation remains our best guess for how the universe grew from nothing to everything in less time than it takes to snap your fingers. And if inflation can happen once, could it happen again? Some models suggest that under the right conditions, a patch of our own universe might suddenly inflate, birthing a new cosmos within ours, a cosmic Russian doll with universes nested inside universes. It's a dizzying possibility, one that blurs the line between science and philosophy. After all, if the multiverse is real, then every imaginable universe might exist somewhere, including ones where the laws of physics allow for life to arise over and over in endless variation. For now, these ideas lie at the edge of what we can test, but they push us to ask deeper questions about our place in reality. Is our universe a lone accident, or one of countless others in an unending cycle of creation? The answer might lie hidden in the faint echoes of the Big Bang, waiting for us to listen closely enough. What if everything we call reality, every galaxy, every law of physics, even the concept of time, is just one version of existence among countless others? This isn't science fiction. It's the multiverse theory, a radical idea born from the math of cosmic inflation. Imagine an endless foam of universes, each bubble with its own unique rules. Some might have gravity so strong stars collapse instantly, others with no atoms at all. In this cosmic landscape, our universe isn't special. It's just one possibility among an infinite number. A single page in a library where every book tells a different story of reality. The real shocker, this might solve one of cosmology's biggest puzzles, fine-tuning. Why do the constants of nature, the strength of gravity, the mass of an electron, seem perfectly calibrated for life to exist? Change any one slightly and stars wouldn't shine, molecules couldn't form, and life as we know it would be impossible. In a multiverse, there's no mystery. With infinite variations, some universes inevitably hit the jackpot, while most remain barren. We're not in a tailored cosmos, we're just the lucky winners of a cosmic lottery. But the multiverse isn't just about physics. It forces us to rethink what science can even explain. If other universes are forever beyond our observation, does the multiverse count as science? Or is it philosophy dressed in equations? Some critics argue it's untestable, a retreat from empiricism. Yet supporters point to subtle clues like odd patterns in the cosmic microwave background that could hint at collisions with other bubble universes. Others suggest the key lies in string theory, where higher dimensions might host alternate realities just millimeters away, separated by folds in space we can't perceive. The most mind-bending twist, if the multiverse is real, there could be versions of you living every possible life. A universe where you never missed that train, another where dinosaurs evolved intelligence, or one where the laws of physics made life impossible from the start. It's a dizzying thought, but here's the catch: we'll likely never know for sure. Other universes, by definition, might exist outside our cosmic horizon, their light forever out of reach. Still, the multiverse pushes science to its limits, blending hard math with existential wonder. Whether it's true or not, it reminds us how strange reality might truly be, and how much we have left to discover. After all, if our universe is just one bubble in an endless froth, what other impossibilities might be out there, waiting in the dark? Black holes have long been painted as the villains of the cosmos, cosmic monsters that devour everything in their path. But what if we've had it all wrong? Instead of being the universe's endpoints, they might actually be its most creative forces. Picture a supermassive black hole at the heart of a galaxy, its gravity so immense it bends space and time around it. Far from just swallowing stars, these giants act like cosmic architects, shaping the very galaxies they inhabit. Their gravitational pull dictates the orbits of stars, funnels gas into swirling disks that ignite new star formation, and even flings matter outward in powerful jets that travel across millions of light years. Without them, galaxies as we know them might never have formed. Then there's Hawking radiation, Stephen Hawking's groundbreaking idea that black holes aren't entirely black. Thanks to quantum mechanics, particles can pop into existence near a black hole's edge, with one falling in and the other escaping. Over mind-boggling stretches of time, this process causes black holes to slowly lose mass, evaporating like ice in the sun. For a typical stellar black hole, that process could take longer than the current age of the universe. But for the smallest primordial black holes, it might already be happening, ending in a final burst of energy, a whisper of light in the darkness. But here's where it gets truly wild. Some theories suggest that when a black hole evaporates, it doesn't just vanish. It might leave behind a seed for an entirely new universe. Inside a black hole's crushing singularity, the laws of physics as we know them break down. Space and time become so warped that some models propose they could pinch off into a separate spacetime entirely, birthing a new cosmos with its own laws and constants. It's like a cosmic Russian doll, our universe nested inside another, which itself might have formed inside a black hole from a parent universe. If that's true, then every black hole could be a doorway to another reality, making the universe not just expanding, but endlessly reproducing. Imagine the implications. Instead of a one-time Big Bang, reality could be a never-ending cycle of creation, where black holes are the engines of rebirth. Dying universes collapse into singularities, only to explode outward as new ones, each with slightly tweaked physics. Some might be lifeless voids, others teeming with structures we can't even imagine. And if life can emerge in just the right cosmic conditions, it might exist again and again across these infinite iterations. Of course, this is still speculation, brilliant math on paper, but far from proven. Yet the idea forces us to rethink black holes entirely. They're not just tombs, they might be cradles, and in a universe hurtling toward heat death or a big rip, that spark of potential, the chance that something new could always begin, offers a strange kind of hope. After all, if black holes really are recycling centers for reality itself, then even in the darkest corners of space, there's always the possibility of something new. The moment you crack an egg into a frying pan, you witness something profound, an irreversible arrow of time at work. No matter how long you wait, that egg will never leap back into its shell. This isn't just a quirk of breakfast, it's a fundamental law of the universe governed by entropy, the relentless march toward disorder. From the shattering of glass to the fading of stars, everything in our reality moves in one direction, forward. But why? The answer lies in the aftermath of the Big Bang, where the seeds of time's arrow were planted in the fabric of existence itself. Entropy began low in the early universe, a state of near-perfect order, with energy and matter distributed almost uniformly. But like a deck of cards freshly shuffled, that order was fleeting. The slightest variations in density allowed gravity to pull matter into galaxies and stars, increasing disorder with every collision, fusion reaction, and explosion. Today, entropy continues to rise, driving the universe toward its ultimate fate, a state of maximum disorder where energy is evenly spread and no more work can be done, the so-called heat death. But here's the twist: entropy isn't just about chaos, it's what makes time meaningful. Without it, cause and effect would blur, memories couldn't form, and the universe would lack any sense of before and after. Could time ever run backward? The laws of physics, strangely enough, don't forbid it. At the microscopic level, particles don't care about time's direction. Equations work just as well whether time flows forward or backward. But on a cosmic scale, entropy's grip is unshakable. Some theories suggest that if the universe eventually collapsed in a big crunch, entropy might reverse, rewinding time like a film played backward. Others imagine parallel universes where time flows opposite to ours, though we'd have no way to observe them. What's truly fascinating is how deeply time's arrow shapes reality. Black holes, the most entropic objects in existence, devour information irretrievably. Stars burn out because nuclear fusion increases entropy, transforming ordered fuel into scattered heat and light. Even life itself is a battle against entropy, with organisms temporarily creating order at the expense of their surroundings. But in the end, entropy always wins. The universe's fate might seem sealed by this irreversible flow, but mysteries remain. Could quantum fluctuations or undiscovered physics alter time's arrow? Or is entropy the ultimate clock, ticking toward an inevitable end? One thing's certain, time's direction isn't just a feature of the cosmos, it's the story of everything, written in the slow unraveling of order and the silent expansion of the void. At the smallest scales imaginable, the universe behaves in ways that defy common sense. Empty space isn't empty at all. Instead, it crackles with energy, a seething foam of particles and antiparticles flickering in and out of existence so quickly they're gone before we can detect them. These are quantum fluctuations, brief disturbances in the fabric of reality where energy borrows itself from nothingness, only to vanish again in a cosmic sleight of hand. It sounds like science fiction, but this phenomenon is as real as the ground beneath your feet. In fact, it might be the reason anything exists at all. Think of the quantum vacuum like a stormy ocean where waves rise and fall unpredictably. These tiny ripples aren't just curiosities, they're the architects of cosmic structure. Without them, the early universe would have been perfectly smooth, leaving gravity with nothing to grip. Instead, those microscopic fluctuations stretch to cosmic proportions during inflation, imprinting their patterns onto the fabric of spacetime. Today, we see their legacy in the distribution of galaxies, woven into vast filaments and voids that trace the outlines of those primordial quantum whispers. But the influence of quantum mechanics doesn't stop there. Some theories suggest these fluctuations could be the spark for entirely new universes. Picture a bubble forming in boiling water. If a quantum fluctuation in just the right spot gained enough energy, it might trigger another inflationary burst, birthing a separate cosmos with its own laws of physics. Our universe could be one of countless such bubbles in an endlessly branching multiverse, each with its own unique destiny. Even more astonishing is the role quantum effects might play in the universe's final act. Traditional thermodynamics says entropy will lead to heat death, a frozen, lifeless void. But quantum mechanics offers a loophole. Given enough time, think trillions upon trillions of years, random fluctuations could, in theory, reorganize energy into a new ordered state. It's like shaking a box of scattered puzzle pieces until, by pure chance, they briefly form a complete picture. The odds are vanishingly small, but in an infinite timeline, even the impossible becomes inevitable. Of course, this isn't a guarantee of cosmic rebirth. Most fluctuations would be too weak or short-lived to matter. Yet the mere possibility hints at something profound. Even in a universe racing toward darkness, the rules of quantum mechanics leave the door ever so slightly ajar. Reality might not end with a whimper after all, just an unimaginably long pause before the next improbable roll of the dice. What does this mean for us? If quantum fluctuations can birth universes or reset entropy, then the cosmos might be far more resilient than we thought. The same chaotic dance of particles that filled the early universe with structure could, given enough time, do it all over again. It's a humbling thought that the fate of everything might hinge on events so small they're invisible, yet powerful enough to shape eternity. Imagine plucking a guitar string. Each vibration creates a different note. Now shrink that string down to a billionth of a billionth the size of an atom, and you've got the basic idea behind string theory. Instead of point-like particles, everything in the universe, from the quarks inside you to the light from distant stars, might be made up of these infinitesimal, vibrating strands of energy. The pitch of their vibration determines whether they manifest as an electron, a photon, or even the elusive graviton, the hypothetical particle that carries gravity's force. It's a radical reimagining of reality's building blocks, one that could finally bridge the gap between Einstein's general relativity and the bizarre rules of quantum mechanics. But here's where it gets mind-bending. These strings don't just wiggle in the 3 dimensions we know. To make the math work, string theory requires extra dimensions, tiny, curled-up spaces hidden at every point in the cosmos, like the folds in an origami sculpture too small to see. Depending on how these dimensions are shaped, they could dictate not just the behavior of strings, but the very laws of physics themselves. Some configurations might produce a universe with strong nuclear forces that bind atoms tightly. Others could render gravity so weak that planets never form. This is the landscape of string theory, a vast array of possible universes, each with its own unique rulebook. That landscape holds staggering implications for the universe's fate. If our cosmos is just one possibility among countless others, its destiny might be written into the geometry of those hidden dimensions. Certain string theory models suggest that dark energy, the force accelerating the universe's expansion, could be tied to how those extra dimensions evolve over time. In some scenarios, dark energy might weaken, allowing gravity to eventually pull everything back into a big crunch. In others, it could grow stronger, leading to a catastrophic big rip. There's even a wild possibility that colliding higher dimensional structures like brains, the theoretical membranes strings attached to, could trigger cyclical universes, with big bangs happening over and over like waves crashing on a shore. Yet for all its elegance, string theory remains controversial. No experiment has yet detected these tiny strings or extra dimensions, and some critics argue the theory isn't even falsifiable, a core requirement for science. But supporters point to indirect clues. If strings exist, their vibrations might leave faint imprints in the cosmic microwave background, or perhaps create microscopic black holes in particle colliders. Others hope gravitational wave detectors could uncover evidence of higher dimensions, like ripples echoing through unseen layers of space. What's undeniable is the sheer ambition of string theory. It doesn't just aim to explain particles or forces, it seeks to unify them all into a single framework, a theory of everything that could reveal not just how the universe works, but why it's structured this way. Whether it ultimately succeeds or fails, string theory has already reshaped our understanding of reality's deepest layers, turning the fabric of the cosmos into a symphony of vibrating strings, each note a possible destiny waiting to be played. The idea that the universe might be a hologram sounds like something straight out of science fiction, but what if it's not just a wild thought experiment? The holographic principle suggests that everything we perceive, the stars, galaxies, even the space between them, could be a projection from a two-dimensional surface at the edge of reality. Imagine watching a movie on a flat screen, only to realize the images aren't just displayed there, they're encoded into the screen itself, with depth and motion emerging from patterns too fine to see. That's the essence of this theory, Our three-dimensional cosmos might be an illusion, a shadow cast by information etched onto a distant boundary we can't even observe. This isn't just philosophical musing. The math behind the holographic principle comes from black hole physics, where scientists discovered something startling. The maximum amount of information a black hole can contain isn't proportional to its volume, but to its surface area. In other words, everything inside a black hole, every particle, every shred of energy, could theoretically be described by data stored on its event horizon, like a cosmic hard drive. Extend that idea to the entire universe, and you've got the holographic principle, the possibility that all the complexity of space, time, and matter might be encoded on a boundary far beyond our reach. But how could this possibly work? Think of it like a pixelated image. Up close, you see individual dots, but step back and they blend into a seamless picture. In the holographic universe, the pixels are tiny quantum bits, Planck-scale units of information vibrating at the edge of space. Their interactions create the illusion of depth, much like the interplay of light and shadow tricks your brain into seeing 3 dimensions on a flat screen. Even time might emerge from this cosmic code, with change being nothing more than information updating frame by frame. The implications are staggering. If the holographic principle is true, it could solve some of cosmology's biggest mysteries. Dark energy, for instance, that mysterious force accelerating the universe's expansion, might not be a force at all, but a side effect of how information is processed at the boundary. The universe's fate could hinge not on the tug of war between gravity and dark energy, but on the limits of how much data that distant surface can hold. And if information can't be created or destroyed, as quantum mechanics suggests, then even the heat death of the universe might not be the end, just a transformation of how that information is stored. Yet for all its elegance, the holographic principle raises as many questions as it answers. Where is this boundary? How does the encoding process work? And if we're living in a hologram, could there be glitches in the code? Places where the illusion flickers, revealing the true nature of reality. Some theories suggest these glitches might exist in the cosmic microwave background, hidden in anomalies that defy conventional explanation. Others propose that black holes are like cosmic debug screens, where the rules break down and the underlying code becomes visible. Whether the holographic principle holds up or not, it forces us to confront a profound possibility. Reality might be far stranger than we've ever imagined. The universe isn't just expanding or evolving, it might be rendering itself into existence, moment by moment, from a hidden layer we're only beginning to glimpse. And if that's true, then the deepest truths about where everything is going might not be written in the stars, but in the invisible script of quantum information itself. Stretching across the entire sky like a faint, glowing tapestry, the cosmic microwave background is the oldest light in existence, a snapshot of the universe when it was just 380,000 years old. Back then, the cosmos wasn't filled with stars or galaxies, but a searing plasma so dense that light couldn't travel more than a hair's breadth before being swallowed again. Then, in a cosmic blink, everything changed. As the universe expanded and cooled, electrons and protons finally combined into atoms, releasing photons to travel freely for the first time. Those ancient photons are still reaching us today, stretched by 13.8 billion years of cosmic expansion into microwave whispers that bathe the entire universe in a near-uniform glow. But look closer, and that uniformity reveals something extraordinary: tiny ripples, variations in temperature no larger than 1 part in 100,000. These fluctuations are the fingerprints of quantum noise from the universe's very first moments, magnified by inflation into the seeds of all cosmic structure. Without them, gravity would have had nothing to grasp, and the universe would have remained a featureless void. Instead, those minute density variations grew over eons, collapsing into galaxies, clusters, and the vast cosmic web we see today. The CMB isn't just a relic, it's a blueprint encoding the universe's past, and if we can decipher it, its future. Yet the cosmic microwave background holds mysteries that defy explanation. Recent ultra-precise maps from missions like Planck and WMAP have uncovered strange anomalies, regions of the sky where the temperature fluctuations don't match predictions. One patch, dubbed the cold spot, is unusually large and frigid, as if something had carved a void into the early universe. Other anomalies suggest the cosmos might be lopsided, with one hemisphere slightly warmer than the other. Could these be statistical flukes, or do they hint at physics beyond our current understanding? Some theories propose they're scars from collisions with other universes in the multiverse, while others suggest dark energy's influence might be more complex than we thought. The most tantalizing possibility is that these anomalies could rewrite our understanding of dark energy. The CMB's patterns are exquisitely sensitive to the balance of matter, radiation, and dark energy in the cosmos. If the anomalies point to a flaw in our models, perhaps dark energy isn't constant but evolves over time. It could radically alter predictions about the universe's fate. A weakening dark energy might one day surrender to gravity, pulling everything back into a big crunch, or a strengthening one could accelerate the expansion beyond all bounds, tearing space-time apart in a big rip. What's certain is that the CMB is far more than a fading echo. It's a dynamic puzzle, a Rosetta Stone for cosmology that connects the universe's fiery birth to its distant destiny. Every new observation peels back another layer, revealing clues about the invisible forces shaping reality. And as we stare deeper into that primordial glow, we're not just looking back in time, we're glimpsing the invisible hand that guides everything, from the smallest quantum flutter to the vast, unfolding fate of the cosmos. Right now, galaxies are crashing into each other all across the cosmos, violent, beautiful dances that reshape the universe. Picture two enormous cities of stars, each hundreds of thousands of light years wide, slowly spiraling toward one another over billions of years. When they finally collide, gravity twists their shapes into unrecognizable forms, flinging stars into chaotic new orbits while vast clouds of gas slam together, igniting bursts of newborn stars. This isn't destruction, it's cosmic recycling on the grandest scale. The Milky Way itself has grown by devouring smaller galaxies, and in about 4 billion years, it'll meet its match when Andromeda comes barreling toward us at 200,000 miles per hour. The result, a colossal merger, a new supergalaxy some astronomers call Milkdromeda, where the night sky, if any night skies still exist, will blaze with unfamiliar constellations. But these spectacular collisions are a temporary phase in the universe's life. As dark energy stretches space ever faster, galaxies beyond our local group are being dragged out of reach, their light stretched to invisibility. In the far future, the era of galactic mergers will end, leaving galaxies stranded in ever-growing voids, their nearest neighbors vanishing over the horizon. No more cosmic car crashes, no more star-making fireworks, just islands of stars growing colder and dimmer as their fuel runs out. This isolation has terrifying consequences for star formation. Galactic collisions are like cosmic fertilizer, stirring up dormant gas clouds and triggering waves of new stars. Without these collisions, galaxies will slowly exhaust their remaining gas, turning from vibrant spirals into stagnant ellipsoids where only long-lived red dwarfs flicker in the darkness. The universe, once ablaze with young, hot stars, will fade into a graveyard of aging embers. And what does that mean for life? if intelligent civilizations arise in these lonely galaxies, they'll face a universe growing colder and darker by the day. The raw materials for new planets and new life will dwindle as star formation grinds to a halt. Worse still, the accelerating expansion may one day rip away the very photons left from the Big Bang, erasing all evidence that there ever was a larger cosmos beyond their own galaxy. Future astronomers might peer into the void and see only emptiness, unaware that countless other galaxies once existed beyond the edge of sight. Yet even in this bleak scenario, there's a strange beauty. Galactic cannibalism isn't just about destruction, it's about transformation. Every collision reshuffles the cosmic deck, creating new configurations of stars, planets, and potentially life. For now, we live in a golden age of galactic interaction, where the universe is still wild, chaotic, and full of possibility. But like all golden ages, it won't last forever. The clock is ticking on the era of cosmic collisions, making the vibrant universe we see today all the more precious. Galaxies spin faster than they should. Stars orbit their centers at speeds that defy the laws of gravity, unless there's something invisible holding them together. That's the puzzle that first revealed dark matter's existence nearly a century ago. Unlike the atoms that make up planets, stars, and us, dark matter doesn't absorb, reflect, or emit light. It's utterly transparent, passing through normal matter like a ghost walking through walls. Yet its gravitational grip is undeniable, shaping the cosmos on scales we're only beginning to map. Think of dark matter as the unseen scaffolding of the universe. Without it, galaxies would fly apart, their stars scattered into the void like marbles rolling off a table. But here's the catch: despite making up 85% of all matter in existence, we still don't know what it actually is. Is it a sea of exotic particles left over from the Big Bang, a cosmic relic from dimensions we can't perceive, or something even stranger, a shadow version of reality with its own hidden physics? The leading candidate, called WIMP, weakly interacting massive particles, are theoretical particles that barely touch normal matter except through gravity. Experiments deep underground, shielded from cosmic rays, have spent decades hunting for them, watching for the faintest tremor as a dark matter particle bumps into an atom. So far, silence, but alternative ideas are gaining traction. Some theories suggest dark matter might be ultralight, more like a diffuse quantum fog than discrete particles. Others propose it interacts with itself through some unknown force, creating intricate structures we've yet to detect. Now imagine if dark matter isn't eternal. What if, over billions of years, it decays into something else? Some models suggest it could morph into dark energy, the very force accelerating the universe's expansion. In this scenario, the cosmos wouldn't just keep expanding. It would explode outward faster and faster as dark matter's transformation supercharges dark energy's push. Galaxies already on the edge of visibility would blink out overnight, their light stretched beyond detection. Structures that took billions of years to form would be ripped apart in a cosmic eye blink. Yet there's another possibility: dark matter might not be monolithic. What if it comes in multiple forms, some stable, some unstable? A fraction decaying into radiation could explain mysterious signals from space, like the excess gamma rays glowing from the Milky Way's core. Meanwhile, the rest might linger indefinitely, anchoring galaxies even as the universe grows colder and darker. The stakes couldn't be higher. Dark matter doesn't just sculpt galaxies, it holds the key to the universe's ultimate fate. If it decays, the cosmos could meet a violent end. If it's stable, the expansion might continue steadily toward a quiet fade out. And if it interacts in ways we haven't imagined, all bets are off. Every telescope, every particle detector, every supercomputer simulation brings us closer to answers, but the mystery endures. One thing's certain: in the grand story of the cosmos, dark matter isn't just a supporting character. It's the invisible hand guiding everything from the smallest dwarf galaxy to the fate of reality itself. Every second, trillions of nearly invisible particles pass straight through your body, and you'd never know it. These are neutrinos, the universe's most elusive travelers, born in the hearts of stars, supernova, and even the Big Bang itself. With almost no mass and no electric charge, they barely interact with ordinary matter, slipping through planets like sunlight through glass. Yet despite their ghostly nature, these tiny particles might hold unexpected sway over the cosmos' grandest structures. Scientists once thought neutrinos were completely massless, moving at the speed of light. Then came the bombshell discovery: they do have mass, albeit vanishingly small, less than a millionth that of an electron. That revelation cracked open a cosmic puzzle. If neutrinos have mass, their sheer numbers could subtly warp spacetime itself. Imagine trillions of particles, each lighter than a feather, but collectively outweighing all the stars in the universe. Their combined gravity might bend the paths of galaxies, nudging them into the vast cosmic web we see today. But here's where it gets even stranger. Some theories suggest neutrinos could be the universe's counterbalance to dark energy's relentless push. While dark energy stretches space apart, neutrinos, with their tiny but measurable mass, exert a gentle gravitational pull in the opposite direction. It's like a cosmic tug of war where one side is a raging giant and the other a persistent whisper. The effect is minuscule, but over billions of years, it might slow expansion just enough to alter the universe's fate. Neutrinos are also shape-shifters in ways that baffle physicists. They oscillate between three different flavors: electron, muon, and tau as they travel, morphing identities mid-flight like a chameleon changing colors. This bizarre behavior hints at physics beyond our current models, possibly tied to hidden dimensions or undiscovered particles. Some researchers even speculate that sterile neutrinos, a hypothetical fourth flavor, could be part of dark matter's mysterious makeup. The most tantalizing possibility: neutrinos might have played a hidden role in the universe's earliest moments. During the Big Bang, an imbalance between matter and antimatter left behind the atoms that make up everything we see. Neutrinos, with their subtle asymmetries, could have tipped those scales, ensuring our existence. Now, they might be writing the final chapter, quietly shaping whether the cosmos ends in fire, ice, or something beyond our imagination. Detecting these phantoms is no easy feat. Experiments like IceCube, buried deep in Antarctic ice, or Super Kamiok, and a tank of ultra-pure water beneath a Japanese mountain wait for the rare flash of light when a neutrino finally collides with an atom. Each detection is a whisper from the distant universe, a clue to forces that shape the past and might yet decide the future. So while dark energy dominates headlines, neutrinos work in the shadows, their influence faint but far-reaching. They remind us that even the smallest players can shape the grandest stages, and in the vast theater of the cosmos, the quietest voices might have the most to say. There's a quiet terror lurking in the fabric of reality itself, one that could rewrite the rules of existence in an instant. Picture the universe as a vast frozen lake. On the surface, everything seems stable, but beneath lies a deeper, more stable state the ice hasn't yet reached. One tiny crack, one quantum nudge in the wrong place, and the entire structure could shatter, collapsing into that lower state with unstoppable force. This isn't just a metaphor, it's the chilling possibility of vacuum decay, a doomsday scenario where the very laws of physics could change without warning. The idea hinges on a quantum quirk, our universe might not be in its most stable configuration. Instead, it could be trapped in what scientists call a false vacuum, a precarious state balanced like a marble resting on the peak of a hill. A single quantum event, perhaps a particle tunneling through an energy barrier, could tip the balance, creating a bubble of true vacuum where the laws of physics are fundamentally different. This bubble would expand at the speed of light, its walls rewriting reality as they pass. Stars, planets, even the atoms in your body would be unmade, replaced by something entirely alien. There'd be no warning, no time to react. One moment, the universe as we know it exists, the next, it doesn't. What makes this scenario so unsettling isn't just the destruction, but the randomness. Vacuum decay could be triggered anywhere, anytime, by quantum fluctuations so rare they might not have happened in 14 billion years, or could happen tomorrow. The trigger might already be racing toward us from some distant galaxy, a wave of annihilation we won't see until it's too late, or it could start right here in some lab experiment or natural process, rewriting the cosmos from the inside out. Yet for all its horror, vacuum decay isn't just science fiction. The math checks out. Quantum field theory allows for such metastable states, and if our universe is in one, the risk is real. Some theories even suggest this might have happened before, that our cosmos is just one in a chain of universes, each collapsing into a new vacuum state with different physical laws. In this view, we're living in the brief calm between storms, a pocket of stability in an eternally shifting landscape. The silver lining: if vacuum decay hasn't happened yet, the odds are staggeringly low. The universe has lasted billions of years without collapsing, suggesting either our vacuum is stable or the dice haven't rolled the wrong way. Still, the possibility lingers, a reminder that existence might be more fragile than it seems. And in that fragility lies a strange beauty. The universe isn't just a static backdrop, but a dynamic, ever-evolving system where even the deepest laws aren't set in stone. Whether that evolution leads to renewal or ruin, though, is a question only time and quantum chance can answer. The Milky Way alone contains hundreds of billions of stars, many with planets in the habitable zone. So where are all the aliens? This is the core of the Fermi paradox, a question so simple yet so profound it shakes our understanding of the cosmos. On paper, the numbers suggest the galaxy should be teeming with civilizations. Even if only a tiny fraction of planets develop life, and an even smaller fraction produce intelligent species, the sheer scale of the universe implies we shouldn't be alone. And yet, after decades of listening, searching, and waiting, the silence is deafening. One unsettling possibility is that advanced civilizations don't last long enough to be found. Imagine a species like ours reaching technological maturity only to annihilate itself with nuclear war, runaway climate change, or unchecked artificial intelligence. This great filter theory suggests that somewhere between the rise of life and interstellar expansion, there's a wall, a challenge so deadly almost no civilization survives it. The haunting question: is that wall behind us, meaning we've beaten the odds, or ahead of us, lurking in our future? But self-destruction isn't the only answer. The universe might simply be too young for widespread intelligent life. Earth took nearly 4 billion years to evolve creatures capable of asking these questions. If most civilizations are just now emerging or haven't even begun, we might be among the first to look up and wonder. In this scenario, the cosmos is still waking up, with humanity as an early voice in a conversation that's only just beginning. Then there's the darker cosmic explanation. Maybe the universe is inherently hostile to long-term survival. Gamma-ray bursts, asteroid impacts, or even the gradual decay of protons could reset the clock on life over and over. Advanced civilizations might rise only to be wiped out by forces beyond their control, their achievements erased before they ever make contact. Yet the silence could also mean we're looking for the wrong things. What if advanced societies don't use radio waves or have moved beyond physical forms into digital existences we can't perceive? Or perhaps they're observing us silently, choosing not to interfere, a galactic prime directive playing out on a scale we can't comprehend. The Fermi paradox isn't just about aliens, it's a mirror. It forces us to ask whether intelligence is a fleeting spark or an enduring flame in the cosmos. Every day we don't find an answer, we're left with a humbling thought. The universe might be far lonelier or far stranger than we ever imagined. Humanity's greatest structures, our cities, power grids, even the internet, are child's play compared to what truly advanced civilizations might build. Imagine a society so powerful it doesn't just harness the energy of planets or stars, but entire galaxies. That's the vision of the Cardiff scale, a cosmic ranking system that classifies civilizations by how much energy they control. A Type I civilization masters its home planet, a Type Roman II commands the output of its star, and a Type Roman III wields the energy of a galaxy itself. Right now, we're not even Type I, but the scale forces us to ask, if intelligence persists long enough, could we defy the universe's darkest predictions? Consider the energy demands of a Type Roman III civilization. To power such a society, you'd need to capture every photon from 100 billion stars, perhaps constructing megastructures like Dyson spheres around each one. This isn't just engineering, it's cosmic alchemy, turning starlight into computation, art, and exploration on scales we can barely fathom. But here's the catch. Dark energy's relentless expansion is already pulling galaxies apart faster than any civilization could bridge the gaps. A Type Roman III society might find its empire fracturing before it reaches full maturity, its stars vanishing over the horizon like ships lost in fog. Yet some theories suggest a way out. Advanced civilizations could exploit the universe's deepest secrets, harnessing black holes as energy sources, or manipulating dark energy itself to slow or even reverse local expansion. Hypothetical technologies like cosmic strings or negative mass could stitch isolated regions of space back together, creating highways across the growing void. More radically, a sufficiently advanced civilization might escape this universe entirely, tunneling through higher dimensions or creating baby universes in labs, a cosmic lifeboat strategy against the heat death of reality. The most profound implication: intelligence itself might become the universe's saving grace. If civilizations can persist long enough to re-engineer the cosmos, the story of existence might not end in cold, empty darkness. Instead, sentient life could become the universe's immune system, fighting entropy with creativity and collective will. Some models even suggest a hypothetical Type Roman IV civilization, one that transcends galaxies entirely, harnessing the energy of multiple universes or rewriting the laws of physics to suit its needs. Of course, this is all speculation. We have zero evidence such civilizations exist, and the sheer timescales involved, billions of years, make the idea feel more like science fiction than science. But that's the power of the Kardashev scale. It forces us to think beyond humanity's fleeting moment, to envision a future where intelligence isn't just a brief spark, but an enduring flame in the cosmic dark. Whether that flame flickers out or grows to illuminate the universe itself depends on questions we're only beginning to ask. What if the universe's inevitable fate could be cheated, not by fleeing to another galaxy, but by leaping backward through time? The idea of escaping cosmic doom by rewinding the clock isn't just science fiction. Hidden within Einstein's equations are strange solutions called closed time-like curves. theoretical pathways that loop back on themselves, allowing travel to the past without breaking the laws of physics. Picture a cosmic Möbius strip where time bends until the future connects with the past, creating a shortcut through history. For a civilization staring down the heat death of the universe or an approaching Big Rip, this could be the ultimate Hail Mary, a way to reset the clock before the end arrives. But time travel isn't as simple as firing up a machine and vanishing into yesterday. The universe has safeguards. Take the infamous grandfather paradox. If you traveled back and prevented your own birth, how could you have existed to make the trip in the first place? Quantum mechanics offers a bizarre fix: parallel timelines. Every decision might spawn a new universe, meaning your actions in the past wouldn't rewrite history but branch it, leaving the original timeline intact. Yet even this raises questions. If a dying civilization jumped back to restart its growth, would it just delay the inevitable, or could it alter the universe's fundamental trajectory? Then there's the energy problem. Creating a stable time loop would require manipulating spacetime on scales that make Dyson spheres look like child's toys. Negative energy, a hypothetical substance that repels gravity, might be needed to hold a wormhole open long enough to traverse it. But negative energy isn't just rare, it might be impossible to harvest in the quantities required. And even if you could, the act of time travel could destabilize the loop, collapsing it like a house of cards mid-journey. Perhaps the most haunting limitation isn't technical but existential. If time travel were possible, why haven't we met visitors from the future? The silence could mean one of three things. Civilizations never last long enough to develop the technology. Time travel is fundamentally impossible. Or most unsettling of all, they are already here, hidden in plain sight, observing without interfering. For now, time travel remains a thrilling thought experiment, a what-if etched into the margins of cosmology. But it forces us to confront a deeper truth. The universe's fate might not just be about where we're going, but whether the past is ever truly out of reach. What if the universe isn't the ultimate reality, but something more like an unfathomably advanced video game, a cosmic simulation running on hardware built by beings we can't even comprehend? This is the simulation hypothesis, a mind-bending idea that's as unsettling as it is irresistible. Imagine a future civilization with computing power so vast they could recreate entire universes, complete with conscious beings who believe their world is real. If that's true, then everything we know, the stars, the laws of physics, even our own thoughts, might just be lines of code in an alien supercomputer. The logic behind this isn't just science fiction. Philosopher Nick Bostrom laid out a chilling trilemma. Either civilizations never reach the technological stage to create such simulations, they choose not to run them, or we're almost certainly living in one. Given the staggering number of potential simulated realities compared to a single, base universe, the odds, he argues, aren't in our favor. Think of it like a vast cosmic casino. If there are trillions of simulated worlds for every real one, chances are you're not holding the winning ticket. But here's where things get really strange. If we are in a simulation, the programmers could rewrite the rules at any moment. Dark energy's acceleration. Just a tweak to the parameters, the sudden collapse of the vacuum, a system update gone wrong. Even time itself might not be fundamental, but a programmed illusion to make the simulation feel continuous. Some theories suggest glitches in quantum mechanics, like particles existing in multiple states until observed, could be processing shortcuts, the universe's way of saving computational power. The simulation hypothesis also flips the script on the universe's fate. Instead of heat death or a big rip, our world might simply be shut down when the experiment ends, or reset like a cosmic reboot. Alternately, the simulation could run indefinitely. its creators tweaking variables to avoid collapse, or even spawning nested simulations within simulations, a fractal reality where no layer is truly base. Of course, there's no smoking gun yet. Some scientists have proposed looking for signs in the cosmic microwave background, like pixelation at Planck scales or anomalies that resemble rendering limits. Others suggest high-energy physics experiments might uncover the universe's underlying code mathematical patterns too perfect to be accidental. But even if we never prove it, the simulation hypothesis forces a profound question. Does it matter if reality is real? The stars still shine, the laws of physics still hold, and the universe's mysteries remain just as compelling. In the end, whether we're in a simulation or not, one truth stands: the universe, real or rendered, is the only one we've got. And that makes uncovering its secrets and our place within it a journey worth taking, no matter who or what is watching. The universe doesn't have to end with a whimper or a rip. It might just take a deep breath and start all over again. This is the heart of cyclic cosmology, a radical reimagining of existence where the cosmos isn't a one-time event, but an endless loop of birth, collapse, and rebirth. Picture a cosmic accordion, expanding and contracting in rhythms so vast they make geological time seem like the blink of an eye. Each cycle begins with a big bang, unfolds into galaxies and life, then gathers back into a scorching singularity, only to explode outward once more, resetting the clock for a new universe with slightly different rules. It's a vision that trades oblivion for eternity, offering a universe that never truly dies, but instead reinvents itself in an infinite dance of creation. What's fascinating is how this idea sidesteps the grim fates of heat death or vacuum decay. Instead of fading into cold nothingness, the universe in cyclic models remains vibrant, its energy recycled in each collapse. Matter isn't scattered beyond recovery. It's compressed, heated, and reborn like a phoenix rising from its own ashes. Even the constants of nature, the speed of light, the strength of gravity might tweak slightly with each cycle, explaining why our universe seems so finely tuned for life. After countless iterations, the math suggests a combination of laws conducive to complexity would inevitably emerge. But how could such a cycle work without violating the laws of physics? The key might lie in dark energy's shadowy cousin, dark matter. Some models propose that as the universe expands, dark matter gradually decays into dark energy, fueling acceleration until, instead of tearing spacetime apart, it triggers a reversal. Gravity, reinforced by collapsing dark matter structures, would then pull everything back together. Another theory, rooted in string theory, imagines our universe as a four-dimensional brain colliding with another in higher dimensional space. These collisions could spark successive big bangs, like cymbals clashing in an eternal symphony. The most tantalizing clue might be hidden in gravitational waves. If cyclic cosmology is true, the violent crunch at the end of each cycle would send ripples through space-time itself, echoes of collapse that might still linger, faintly imprinted on the cosmic microwave background or detectable by future observatories like the Laser Interferometer Space Antenna. These waves could carry fingerprints of the previous universe, a cosmic palimpsest waiting to be decoded. Yet cyclic cosmology isn't without its paradoxes. Would information, the arrangement of particles, the memory of stars survive the collapse, or is each universe a blank slate? Some theories suggest quantum entanglement might preserve subtle patterns across cycles, like a message passed between iterations. Others argue that entropy, the universe's relentless march toward disorder, would still accumulate over multiple cycles, meaning even an eternal cosmos might eventually exhaust itself. For now, cyclic models remain speculative, but they offer something rare in cosmology: hope, not just for the universe, but for our place within it. If existence is a loop, then every ending is also a beginning, and the story of the cosmos isn't a tragedy, but an epic without finality. Whether the evidence ever confirms it, the idea alone reshapes how we see reality, not as a fleeting spark, but as a flame that never truly goes out. What if death isn't the end, not just for us, but for the universe itself? Dive into the quantum realm, and you'll find a theory so strange it turns cosmic doom on its head. In the many worlds interpretation of quantum mechanics, every possible outcome branches into a new universe. Flip a coin, and somewhere it lands heads, and somewhere else tails. Now stretch that idea to cosmic scales. If every quantum event spawns alternate realities, then there must exist timelines where the universe avoids heat death, escapes vacuum decay, or even dodges the Big Rip entirely. Here's the mind-bending twist. If consciousness can only persist where conditions allow it, then from any subjective viewpoint, the universe might never reach true annihilation. You'd always find yourself in a branch where existence continues, no matter how improbable. This isn't just philosophy, it's a loophole in the fabric of reality. Think of it like a cosmic game of survival, where the odds are astronomically against you, yet you always land on the winning path. Even as trillions of universes succumb to entropy or collapse, your experience would be the one where life, against all probability, endures. Physicists call this quantum immortality, and while it sounds like science fiction, it emerges from the cold math of quantum theory. The catch: there's no way to test it. You can't observe the universes where you or the cosmos cease to be. Critics dismiss the idea as a thought experiment gone rogue, a trick of perspective rather than a physical law. After all, if every possible outcome exists, why should consciousness privilege survival? Yet supporters counter that the very nature of observation might tether us to the timelines where we persist. It's like a cosmic version of the anthropic principle. We're here to ponder the universe because in the branches where we couldn't, no one's left to ask the question. The implications are dizzying. If quantum immortality holds, the universe's fate isn't a fixed-in point, but a kaleidoscope of possibilities where life, against all odds, always finds a way. Dark energy could rip space-time apart in most branches, but somewhere, a version of reality slips through the cracks, threading the needle of survival. It's not quite cheating death, it's sidestepping it entirely, riding the quantum wave into perpetuity. Of course, this offers little comfort for the universe at large. Countless versions of reality would still meet grim ends, their stars fading to black, but for the threads where consciousness endures, the story never truly stops. Whether that's a profound truth or a trick of the math depends on how deeply you trust the quantum rabbit hole. One thing's certain: in a multiverse of infinite outcomes, even the impossible becomes inevitable somewhere. The real question is whether we're part of the threads that make it, or just the ones imagining we could. What if consciousness isn't something the universe has, but something the universe is? This isn't just poetic musing, it's a hypothesis that flips our understanding of reality on its head. Most scientists treat consciousness as an emergent property, a byproduct of complex brains arranging atoms in just the right way. But a growing chorus of physicists and philosophers argue the opposite. That awareness might be as fundamental to the cosmos as space, time, or gravity. In this view, the universe isn't just a cold, mechanical system, it's a vast, interconnected web of experience, with mind and matter two sides of the same cosmic coin. Think of it like this: when you watch a sunrise, your brain doesn't create the colors and warmth you perceive, it translates them from an external reality. But what if that translation is just one layer of a deeper, more pervasive consciousness? Some theories, like panpsychism, propose that even particles have a rudimentary form of experience. An electron might not ponder philosophy, but it could possess a faint, flickering awareness, a subjective, what it's like to be that electron. Combine countless such experiences across the fabric of space-time, and you get something resembling a universal mind, a grand tapestry of perception woven into existence itself. The implications are staggering. If consciousness is baked into reality's foundation, it might not just observe the universe, it could shape it. Quantum mechanics already shows that observation affects the behavior of particles, collapsing probabilities into definite outcomes. Could this be a hint that awareness isn't passive, but an active participant in creation? Some interpretations suggest the universe might choose certain paths over others, steering its own evolution through a form of cosmic will. This idea blurs the line between physics and metaphysics. If the cosmos has intentions, however subtle, could dark energy's acceleration or quantum fluctuations reflect something like preference? Might black holes, galaxies, or even the vacuum of space itself harbor fragments of a greater awareness? It's a controversial leap, but one that resonates with ancient traditions and cutting-edge theory alike. From Hindu concepts of Brahman to modern integrated information theory, which quantifies consciousness as a property of complex systems. Of course, skepticism runs deep. Critics argue that attributing awareness to the universe is anthropomorphism on a grand scale, projecting human traits onto indifferent physics. Yet proponents counter that dismissing the idea outright might be its own kind of bias, a refusal to consider that materialism, for all its successes, could be incomplete. After all, if consciousness truly emerges from mere matter, we still have no convincing explanation for how subjective experience arises from objective particles. Perhaps the truth lies somewhere in between. The universe might not think in any way we'd recognize, but its laws could allow for forms of awareness far stranger than we imagine. Whether that means the cosmos has a destiny it's subtly guiding, or simply that existence is richer than our models can capture, remains one of the deepest mysteries of all. What's certain is that the question itself reshapes how we see reality, not as a clockwork mechanism, but as something alive with possibility, waiting to be understood. Imagine a civilization watching the stars around them fade, galaxies pulled beyond the horizon by dark energy's relentless push. Now picture them turning not outward, but inward, seeking refuge not in distant corners of space, but in hidden layers of reality itself. This is the audacious promise of interdimensional escape, the idea that when the universe becomes too vast, too empty, or too hostile, the answer might lie in dimensions we can't yet perceive. String theory paints a cosmos far richer than the three dimensions we know, with tiny, curled-up spaces at every point, like the folds of an origami sculpture too small to see. If these extra dimensions exist, could they become the ultimate lifeboats for a species facing cosmic extinction? The math is tantalizing. In brain-world models, our entire universe might be a three-dimensional brain floating in a higher dimensional bulk. Just as a sheet of paper is flat to an ant but part of a larger space to us, our reality could be one slice of a multidimensional cosmos. Under the right conditions, energy or even matter might leak between brains like ink seeping through porous fabric. For a civilization mastering such physics, crossing into another brain wouldn't just be exploration, it could be survival. A dying universe, its stars cold and its energy spent, might be abandoned for a younger, richer reality next door. But interdimensional travel isn't just about finding new space, it's about rewriting the rules. higher dimensions could harbor physics unrecognizable to us, with alternate constants, forces, or even flows of time. A brain where gravity is stronger might allow black holes to form more easily, while one with weaker nuclear forces could render stars impossible. The risks are as vast as the possibilities. A misstep could unravel matter, trap travelers in timeless voids, or trigger collapses in both the origin and destination universes. Yet for a civilization with nothing left to lose, the gamble might be worth it. The wildest twist, we might already have evidence of these hidden realms. Some theories suggest dark matter's ghostly influence could be particles from a neighboring brain, barely interacting with ours except through gravity. Others propose that rare, high-energy cosmic rays are the fingerprints of brain collisions, cosmic fender benders shaking the fabric of reality. If true, the portals to these dimensions might not need to be built, but found, hidden in the violent hearts of particle accelerators or the remnants of supernova. Of course, this is all speculative, dancing on the edge of science and imagination. But that's the power of interdimensional thinking. It forces us to confront the universe not as a fixed stage, but as a labyrinth of possibilities. Whether escape is feasible or not, the mere idea reshapes our vision of the future. The cosmos might not end with a fade to black, but with a step sideways into the unseen, the untested, the unimaginable. Black holes aren't just cosmic dead ends, they might be the ultimate creators. When two of these gravitational monsters collide, the energy released doesn't just ripple space-time, it could tear a hole in reality itself. According to some radical theories, the extreme conditions inside a merging black hole might briefly open a portal to an entirely new universe, a baby cosmos budding off from our own like a branch from a tree. The math is speculative but stunning. Inside the singularity's infinite density, the laws of physics as we know them break down, potentially allowing a new spacetime to inflate with its own unique constants. It's as if the universe encoded an escape hatch into its most destructive phenomena. But black holes aren't the only laboratories for cosmic creation. Imagine a tabletop experiment so precise it manipulates quantum fields at their most fundamental level. In principle, if you could concentrate enough energy into a microscopic space, say, by smashing particles at unimaginable speeds, you might trigger a phase transition in the vacuum of space itself. Like poking a needle into a soap bubble, the right quantum nudge could cause a bubble of new spacetime to nucleate and expand at light speed, birthing a universe with its own physics. The catch, you'd need energies rivaling the Big Bang, or a way to amplify quantum fluctuations artificially. For now, it's the domain of particle accelerators far beyond our current tech, but not necessarily forever. Here's the twist: if we could engineer such an event, the new universe would be forever sealed off from ours, its fate unknown. We wouldn't be gods so much as cosmic gardeners, planting seeds we could never witness sprouting. Some models even suggest these artificial universes would inherit slight variations in their physical laws from their parent, meaning each attempt could produce a cosmos where stars never form, or one where life arises more readily. It's the ultimate gamble, a roll of the quantum dice with stakes spanning eternity. The most profound implication isn't just survival, it's legacy. If intelligence can birth universes, then the great filter confronting civilizations might not be extinction, but transcendence. A species facing heat death could choose to become more than inhabitants of a dying cosmos, transforming into architects of fresh realities. The universe's story wouldn't end with entropy, but with an infinite branching of possibilities, each new cosmos carrying forward the potential for life, thought, and perhaps even its own experiments in creation. Of course, this hinges on physics we've barely glimpsed, yet the mere possibility reshapes our place in the cosmic order. we're no longer just passengers on a ride to oblivion. We might be the unlikely scribes of the universe's next chapter. Whether that chapter gets written depends not just on the laws of nature, but on whether intelligence can outthink time itself. Imagine holding a cosmic lever. One pull could slow dark energy's grip, buying trillions of years for civilizations to thrive. But here's the dilemma: who gets to decide? The power to tweak the universe's fate isn't just a scientific challenge, it's an ethical minefield. Take dark energy. If we weakened it, we might save our local group of galaxies from isolation. But what about distant regions where life depends on expansion to avoid catastrophic collisions? Altering fundamental forces could rewrite the rules for everyone, everywhere, with no undo button. This isn't just engineering, it's playing architect to reality itself, with consequences echoing across space and time. Consider the stakes for other civilizations. Right now, we have no way of knowing if intelligent life exists beyond Earth, but statistically, the universe should be teeming with it. If we tamper with cosmic constants to extend our own survival, we might inadvertently trigger a chain reaction that dooms others. Picture a species halfway across the cosmos whose existence hinges on dark energy's current strength. Our well-intentioned adjustments could collapse their star systems or disrupt delicate biological processes we can't even conceive of. The universe doesn't come with error messages. A single miscalculation could erase countless futures without warning. Then there's the question of hubris. Human history is littered with examples of well-meaning interventions that backfired, introducing invasive species to new ecosystems, or releasing engineered genes without understanding long-term effects. Scaling that up to cosmic levels introduces risks we can't possibly model. What if suppressing dark energy today leads to a vacuum decay catastrophe tomorrow? Or worse, what if our attempts to fix the universe reveal we've disrupted a natural cycle essential for cosmic rebirth? Some theories suggest the universe's expansion and contraction might be phases of a larger process we don't yet understand. By intervening, we could be interrupting a heartbeat that sustains existence itself. Yet doing nothing carries its own moral weight. If civilizations have a duty to preserve knowledge and consciousness, then passively accepting heat death might be the greater sin. Philosophers like Nick Bostrom argue that the ethical imperative to prevent suffering extends beyond Earth. If we can act to avert cosmic extinction, we must. Imagine a future where humanity masters stellar engineering, only to watch helplessly as the cosmos darkens, knowing we had the tools to act but chose restraint. The weight of that inaction could haunt our descendants for eternity. Perhaps the answer lies in balance, not reckless intervention, but cautious stewardship. Instead of rewriting physics, we might seek to harmonize with the universe's natural rhythms, like a surfer riding a wave rather than trying to stop the ocean. Technologies that harness existing phenomena, think Dyson spheres tapping stellar energy or black hole farming, could extend our timeline without altering the cosmic fabric. Or we might focus on preserving consciousness in forms resilient to entropy, like digital minds capable of hibernating through eons between bursts of activity. The deeper truth: this debate forces us to confront what it means to be custodians of existence. Whether we choose to act or abstain, the mere possibility of shaping the universe's fate binds us to a responsibility far beyond our planet. The stars won't judge our choices, but they'll bear the consequences, and so will every civilization, known or unknown, that shares this cosmos with us. The question isn't just what we can do, it's what we owe to the universe that made us. Even as the universe cools toward its final fade, there's something defiant in the human spirit, an insistence that our story shouldn't vanish without a trace. Think of the cave paintings at Lascaux surviving 30,000 years to whisper across millennia. Now imagine scaling that ambition to cosmic proportions. Scientists have theorized ways to etch our knowledge into the fabric of reality itself, using particles so stable they could outlast stars. Take protons, for instance. If they truly never decay, as some models suggest, encoding data in their quantum states could create a library with a shelf life measured in trillions of years. Picture etching the sum of human art, science, and history into the spin of atomic nuclei, a message in a bottle adrift in the slow march toward entropy. But protons might not be the ultimate time capsule. Black holes, those voracious devourers of information, could paradoxically become the universe's most durable archivists. According to physicist David Deutsch, the event horizon of a black hole could store data in holographic form, preserving it even as the cosmos outside grows cold and dark. The math is dizzying. A single black hole could hold more information than all the books ever written, compressed into a space smaller than an atom. Future civilizations, or whatever evolves beyond us, might mine these gravitational vaults, extracting knowledge long after the last star winks out. Yet durability isn't the only challenge. How do you make a message intelligible to beings separated from us by eons of cosmic evolution? Linguists and physicists have wrestled with this for decades, from the symbolic plaques on the Pioneer probes to the pulsar maps etched into the Voyager golden records. A universal language might need to be rooted in math or physics constants like pi or the hydrogen line frequency, but even these could be ambiguous across unfathomable timescales. Some propose self-assembling algorithms coded into quantum fluctuations or gravitational waves that could reconstruct their meaning like a cosmic Rosetta Stone. The deeper question isn't just technical but philosophical: what's worth preserving? The complete works of Shakespeare, the structure of DNA, the equations of general relativity, or something subtler, the emotional weight of a symphony, the brushstrokes of a painting, the collective memory of a species that once looked up and wondered. Perhaps the most poignant legacy wouldn't be raw data, but proof that curiosity existed at all. In a silent, cooling universe, even the faintest scratch on the walls of reality would whisper, "We were here." And if no one ever finds these messages, the act of sending them still transforms us. To etch our mark on eternity is to reject the idea that existence is meaningless, to declare against the void that our brief flare of awareness mattered. The universe may forget, but in trying to be remembered, we've already changed what it means to be alive. The universe's grand finale is still unwritten, a mystery suspended between icy silence and infinite renewal. Every theory we've explored, from dark energy's relentless push to the holographic whispers of alternate dimensions, isn't just about predicting an ending. It's about understanding the cosmos as something alive, dynamic, and full of surprises. Whether the universe fades into darkness, collapses into rebirth, or unravels into something beyond our imagination, one truth remains: the act of searching for answers binds us to the stars themselves. Think of humanity's journey as a single candle flickering against the cosmic night. We've charted galaxies, decoded the light of ancient stars, and glimpsed the quantum fabric beneath reality. Yet the more we learn, the more we realize how much lies beyond our grasp. Dark energy could be a temporary phase, or the first note in a symphony we can't yet hear. Black holes might be tombs or cradles for new universes. The uncertainty isn't a flaw, it's the universe's invitation to keep exploring. What makes this quest so profound isn't just the science, it's the stories we tell about our place in the void. Ancient cultures saw the cosmos as a cyclical dance of creation and destruction. Modern physics echoes that intuition, not with myths, but with equations that hint at cosmic rebirth. Whether through cyclic cosmology, multiverses, or some undiscovered physics, the idea that existence might continue in some form offers a strange comfort against the vast unknown. Yet, even if the universe's fate is inevitable, our response to it defines us. Do we resign ourselves to oblivion or strive to leave echoes in the dark? From time capsules etched into protons to civilizations harnessing black holes, humanity's legacy might not be in stopping the end, but in ensuring our curiosity outlasts it. The universe doesn't owe us immortality, but it has given us the tools to chase it. So here's the real question: does the destination matter if the journey transforms us? Every telescope pointed at the sky, every equation scribbled on a chalkboard, every debate about dark matter or quantum foam, they're all part of a conversation spanning generations. We're not just observers of the cosmos, we're participants shaping its story even as it shapes ours. Now it's your turn. Which cosmic fate feels most compelling or terrifying? Do you see the universe as a fleeting spark or a flame that never truly dies? Drop your thoughts below, and let's keep this conversation as boundless as the cosmos itself. After all, the universe's greatest secret might be that the search for answers is what makes us stars in human form.